All right, we'll just go ahead and start here. Today and for the rest of the semester, we're going to be focusing on searching and sorting algorithms. This is our last module, and it will take maybe a week or two. So we'll continue it after the break. But the reason that we focus on these things is because they're a huge part of computer science, so much so that we have now diverging branches, like data science and stuff like that. And the two fundamental operations in data, data processing, are searching and sorting. Generally, we refer to searching as you're searching for a needle in a haystack. You've got a collection of things, and you're searching for one particular one based on some criteria. Sorting, again, you've got a collection of things, and then you want to sort them by some criteria. That might be multiple criteria or a combination of criteria. And these form the basis of pre-processing steps to many other algorithms. Some algorithms will assume that it's in order, or assume that it's sorted. Now we proceed. Well, as a first step, of course, you've got to make sure that it's in order, and so you've got to sort it. Also, it provides a large variety of algorithms, right? So there are at least 2 dozen sorting algorithms, each with a different property, each with a different strategy, etc. And so it's really popular to look at these two things because it gives you different algorithmic strategies, okay? So to start out with, we're going to do a demonstration here. We're going to simply write a program or write a function to search a collection for a particular element. Now, before we even begin, that is really general, right? What do we mean by a collection? Right? Collection, right? What do we mean by that, right? Do we mean an array, right? A list, set, right? Whatever we're meaning by that, right? What do we mean by a particular element or searching for a particular element, right? Are these integers, doubles, right? Are these students, right? Or books, right? What criteria? What criteria, right? For example, if you were searching for books, you could search for a particular book with a particular ISBN or a highest rating, right? Et cetera, et cetera. Okay? So even this simple problem of searching through a haystack to find a needle has a huge variety. We're going to have to answer these questions when we actually program it. But before we program it, let's take a look at what we mean more generally, right, by searching. I'm going to bring in, let's see, where are we? Oh, it's not here. I thought it was here. So over here then maybe. There it is. All right. So this is not code, right? This is what's called pseudocode. This is fake code, okay? And the reason that we like pseudocode, fake code, is that it abstracts away the idea of an algorithm from any particular programming language. Could you write something like this in C? No. Could you write this? Oh, you could write something like this in C, but you couldn't write these exact words. For example, in my pseudocode, I always strive to have these vertical lines, and you can get those vertical lines in an IDE by collapsing a block of code, but you can't get it by typing, right? None of the languages that we've looked at so far supports the for each keyword, right? Instead, we have a traditional for loop or we have an enhanced for loop. even the input and the output, right? This is not necessarily a function, this is an algorithm. The input is a collection. Well, collection, what does that mean? A list, a set, an array, right? Of elements. What are these elements, right? I have no idea. They're integers, they're things, right? I'm abstracting away all of the details so that I can talk about the algorithm itself. And a key element here, e sub k. Another thing to notice here, in my pseudocode, I am numbering things like mathematicians do, starting at 1. Computer scientists don't do that. They start at 0. Yet another like red flag that this is not code. This is pseudocode. And our output here, not our return value, but our output is an element such that it matches the key, or if there's no such element, then we return this flag value phi. Right? Now in Java, I would return something, I don't know. In C, I might return null, I might return -1, I might return a whole bunch of different things. Here, I am using some math to abstract away from those language-specific things. All it's doing is for each element in the collection, it checks to see if it's equal to the key element. The first element that you find, it stops and outputs or returns a sub I. Otherwise, if you get through the entire collection and you don't find anything that matches the key element, then you end up outputting phi, right, to indicate an unsuccessful search. Now let's take this and actually implement it in C. Right? This is called linear search, and we'll understand why here in a moment. Now, because I'm in a particular programming language, I have to answer those questions. Right? What am I searching? So let's call it linear search. Right? And what am I going in C? The only thing that we've covered so far that is a collection is an array. Right? Now, I chose to do integers here, but of course you could have changed this so that it's doubles. Right? Now you're searching an array of doubles. You could have changed this so that you're searching an array of strings. Right? I'm going to keep it simple and just search an array of integers. Now, because this is C, what else do I need to pass in? The size. I'll just use n. And because this is my haystack, I need my needle. I need my key. So I'll have an integer key here. Okay. Now, what should my return type be here? Let's document it, because oftentimes you write documentation first in order to clarify what you're actually doing, right? So searches the given array of n integers for the key value, right? Returns blank blank upon success, right? Returns blank blank if no such element exists, right? So you've done this before in Hack 7, right? Contains. Here's your array, here's my key. Does it contain? In that case, you are returning basically a Boolean, right? Yes, it does contain that element. No, it does not contain that element. As an alternative, what could we do? All right, so return an int representing the index, returns the index of key upon success. Now, if I chose that route, what would I have to return if no such element exists? Could I return 0? False, I didn't find it. That means that I found it at the first location, right? So what would a value be for an index that indicates this ain't working? -1, right? Or any negative for that matter, right? Because in C and in Java, we do not have negative index values. In another language, like Python, we couldn't do that because Python does have negative index values. It just wraps around back to the beginning or back to the end if it's negative, right? We'd have to choose a different implementation. But the pseudocode for doing it would be exactly the same, okay? All right, so this is pretty straightforward to do error handling. For int I equals 0, I is less than n, I plus plus. If the ith element is equal to the key, then I'll return I, the index at which I found it. Otherwise, if I get down to the end, I'll return -1, right, if no such element exists. Now, that's what we're going to go with here. But what is another alternative? Think C. What else does C have that Java doesn't have? Pointers. What if instead I decided I'm going to return a pointer? I found it right there, and I'm pointing to it. It's right there. They're in that memory location, right? I would then end up returning what? Ampersand array sub I. And down here, what would I return for for an unsuccessful search in this case? Null, the only thing I can, right? Undo, undo, undo. We're going to keep it simple and keep it like this. There. Now, I need a test case here to make sure that it works. So, like all my test cases, I'm going to randomly generate it. I'm going to random.org here, and I just want some numbers. Integer generator, one column. Can I separate it by? Okay, I can't. I only want 10, between 1 and 100. Okay, that's good enough. Now, I'm going to have to cut and paste this and modify it. I don't know. Can I change the end line character to, come on, a space, and only in my highlighted region. Can I get this done easily? Place. I don't want to do that. Okay, so, nope. All right, never mind. I wanted to do it fancy, but I can't. Undo. Oh, there we go. Redo that. Space, space, comma, 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 and there. And go back, go back, go back, and go back. There we go. Now I've got my test case. Let's make sure it works by searching for a particular key. For example, what if my key element was 17? Where would you expect to find it in that array? At index 0? Okay. So if, let's call int index is equal to linear search of my array of size n, searching for that particular key. If the index is greater than or equal to 0, then that means it was successful. Printf found %d at index %d and the line, and I'm finding the key at index index. Right? Otherwise, if it's negative, of course I can't access it, I can't print it. And so I will say printf unsuccessful search. Right? And the line and be done. Okay? So let's make sure that this works, right, for this very simple example. GCC demo compiles with no errors. Found 17 at index 0, just as we predicted. What else should I check for to make sure that this works? What about another one that's in the middle? 97, that would be found at 0, 1, 2, 3, 4, 5, index 5, all right, verified. Let's check out another extremal element, the one at the end, 62. Right? That should be found at index 9 because there are 10 things in there, right? And we found it. Are those the only thing I should test for? What else am I not testing here? Not in the array, an unsuccessful search. So let's do that. Good, all right. I have a reasonable expectation here that this works. Now, I did try to put together a demonstration here with huge random arrays, and the computer's too fast. I can't get it to show up. So instead, what we'll do is we'll analyze this algorithm with respect to the pseudocode here, instead of giving you a demonstration of this. First of all, what work does linear search do? Search do. All right? So let's look at it from the perspective of this pseudocode right here. Okay? So it's doing a lot of work right here, right? But what should we focus on? Well, the for each loop, right? It's doing a lot of things. It's doing something for each element in the array. Now, if I actually looked at the code here, then there are several things involved. There's an initialization which is done once. There is a comparison to see if we should continue the loop. There's an addition here in order to increment I towards our terminating condition. I generally don't want to look at those things, though, because I don't want to look at control structures. I want to look at what the control structures are doing inside of the control structures. All right? So what are we doing here? We're doing a comparison. Right? We're actually doing several things. We're actually looking at a memory location and loading it up in a cache And if it's not there, then we have what's called a cache miss, and we have to go out and find it in the memory, load it up all the way through the cache, and that can be quite expensive if you're talking about lower level details. That's an engineering thing. We want to look at this from a general algorithmic perspective here. So what I'm going to do is I'm going to focus on this thing right here, the comparison on line 2, right? So my quantification for work here will be comparisons. And in particular, the one on line 2 of the pseudocode. Okay. My next question is going to be, how many comparisons are performed? Question mark. Right? Now, I gave you a variety of tests over here. Right? We searched for the first element. How many comparisons would it have made in that case? Find it right the first place that you were looking for it. 1. What about 97? I'd have to make a comparison here, 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 3, 4, 5, 6 comparisons to find what I was looking for. And then I would stop because I don't go on in this algorithm. I return immediately. Okay? What about that last one right there, 62? I had to make 10 comparisons. What about 42? I also had to make 10 comparisons. So there are different perspectives here. You can think about the best case. The best case is going to be 1 comparison. You find it at index 0, right? You find it at the first location that you looked at, right? Now, can you always assume the best? Are you always going to assume that you get lucky and you always find it the first place you look for it? No, life doesn't work like that. So let's be pessimistic. What is the worst case? Right? Now think about this more generally. Suppose there are n elements in the array A. Okay? Don't just think about it as the one that we looked at and there are 10 elements. Think about it more generally. What if there are 1 million elements in there? What if there are 10 million elements? What if there are 1 billion elements in there? The worst case is either you find it the last location, last index, or unsuccessful search. In both of those cases, what would you end up doing? How many comparisons? N comparisons. All right? Now, just as we can't always assume the worst, sometimes we don't want to think about always assuming the worst, or so we can't always assume the best. Sometimes we don't want to always assume the worst. You can look at this from an average case. Right? Now, that goes beyond the scope of this course, but what you would do is you'd define a probability distribution on the successful search for each location. You would try to maximize that probability, find that it's going to be maximized when it's uniform, add up all of these things, do some algebra. At the end of the day, you'd end up with something that looks like this. Oops. There we go. So what is that average case? A naive way of looking at it would be the worst case plus the best case, and then you take the average, divide by 2. What I'm going to do is I'm going to simplify this even more. N divided by 2 plus 1/2. And then I'm going to take this 1/2 and I'm going to ignore it. Right? Okay, and we'll understand why I'm going to ignore it here in a second. Tell me about these two functions. All right, first of all, let's go ahead and ignore the best case scenario here. But tell me about these two functions. Tell me about n and tell me about n divided by 2. What kind of functions are they? Let's graph them. Come on, snap, there we go, n. And up here would be the number of comparisons. Okay? So as n tends towards infinity, as your array sizes get larger and larger and larger, what is the behavior of the amount of work that you end up doing? So one of them is going to look like this. Not perfect, but there we go. N. Now what does 1/2 n look like? You graph that? Oh no? All right. I'll graph it for you. It's going to look like that. 1/2 n sitting out front. Okay, 1/2 over there. So the only difference is what? The slope. Okay. Now put on your calcats, right, and tell me. Well, first of all, tell me what these functions are. They're what? Linear. They're both linear functions, right? Both of them are linear functions. Right? It's just that one has a constant coefficient of 1, and the other has a constant coefficient of 1/2. At the end of the day, does that matter? Probably not, because there's another hidden coefficient out here called c. Right? C is quantifying the amount of time required to actually do a comparison on your computer. That constant changes if I move it over to your computer, or my computer, or if I upgrade, right? C then becomes, now it's twice as fast, so C divided by 2. Right? Oh, now it's 10 times as fast, so C divided by 10. Right? It takes less time and less time as hardware improves. But nothing about this algorithm changed. This algorithm was the same 20 years ago, 1,000 years ago, as it is today. Right? The only thing changing is this constant out front of how much work we can do in the same amount of time. So from that perspective, there's really no difference between these, because all I have to do is take this 1/2 and move it over here into C. And I've got n and n. Here's another perspective, the calc perspective. What is the rate of growth? Rate of growth of a function. How do you quantify that in calculus? First derivative. And then the rate of the growth is the second derivative, etc. Right? What's the first derivative of n? 1. What's the first derivative of 1/2 n? 1/2. Right? In other words, they're both constant rate of growth. Now you can take off your calcats and look at it from an algebraic perspective. Right? What if I went from a size n up to 2n? If n took time t, and t is just general, right? It took 10 seconds, it took 20 seconds, it took 5 nanoseconds, it doesn't matter. Right? If I double the size, right? This is double-sized array. Right? What would you expect the time to take now? 2t. If I increased it tenfold, an order of magnitude up, right, then you would expect it to take 10t time. Right? Every time I double it, or every time I increase an order of magnitude, it grows linearly. Right? The rate of growth is constant for both of them. Right? In other words, it doesn't matter if you look at it from the worst case and the average case scenario, it's going to be linear. Thus, why we call it linear search. Okay? Now, can we do better? Okay? And let me show you a trick. This is a trick. In fact, you know this trick already. So you play the number game. In fact, you programmed this in lab 3, I think, or maybe 4. Right, whatever the loop introduction lab was. I'm thinking of a number 1 to 100. What should be your first guess? I'm going to tell you higher or lower. 50. Why did you go with 50? You cut it in half immediately, right? And I'll say it's higher. I wasn't actually thinking of a number, so we're not going to play the game. Right? I forgot to think of the number. But anyway, you cut it in half. So what if I told you that the array, not that one, where's my array? My sorted array, there we go. What if I told you that the array was sorted, right? Suppose that you're search for 42, right? You do the same trick. You look at the middle element here, which is why it's highlighted in green there. Right? And it says 12. Well, that's not the thing I'm looking for, is it? Right? So where do I search for next? Do I even bother looking at the left half of this array? No, because the thing I'm searching for is greater than 12. Right? So it's going to appear on this side, if at all. Right? Essentially what I've done is I've cut this array in half with one comparison. Okay? If I had done linear search, I would have to do 1, 2, 3, 4, 5, 6, 7, 8. 8 comparisons. And with just one comparison, I've gotten rid of half of the array. Okay? So let me mark that. Now our new array is of this size. There are only 5 elements left. Do the same trick. Look at the middle element, 105. Well, is that the thing that I'm searching for? No. So what I do is I search in the left half now, right? This and this, right? Because I've effectively cut out this part, just like I cut out this part over here, right? 2 comparisons, and now it says now it's of size 2, which is less than 1/4 of what it was originally. Now, what's the middle? Well, there's no middle element of 2 elements, so you end up comparing it with 42, and you only had to do 3 comparisons, 3 comps comparisons, versus the 8 comparisons that you would have to do with linear search. Right? That's actually really cool, right? Because we can have an exponential speed up now, right? Let's codify this, because the next thing we're going to do is we're going to implement it, okay? Let's understand that process, right? So first of all, I'm going to keep track of 2 indices, left and right. And initially, where are they? At the beginning and at the end. Those 2 indices will help me to find the middle index here, M. Middle index, right? How do I find that index? In this case, it would be 5, right? But in general, if you have a number line here and you've got 2 numbers and you want to find the one right in the middle, what is that? A plus B divided by 2, the average. Right? So left plus right divided by 2. Right? Let's move this up a little bit to give myself some more room. Okay? All right. Well, now I've found my middle index. So I check, is that the thing I'm looking for? If the array of M is equal to my key, then I'm done, right? Done. Output what? Where did I end up finding it? M. Output M. Okay? Otherwise, that's not the case. I need to determine, should I go left or should I go right? Okay? So let's take a look at if I should go left. If the key element is less than A sub M, then where do I need to go? Key element would be less than this guy, so I need to go left. Now, how do I end up doing that, by the way? Move the right index. Oop, I don't want to move all of that. Move the right index over where? 4. Okay. Yeah, I've screwed it up. I should go back. Undo, undo. All right, there we go. I'll move the right index over to 4. Right? Now, why 4? Because you've already checked this one. You don't need to check it again. So the right index ends up being M minus 1. 1 right before it. All right, else if. Else if. Now, the key element, the only other possibility here is that the key element is greater than A sub M, in which case we go to the right. And we would end up updating the left index to M plus 1. Left is equal to M plus 1. Okay? Now we take this entire thing and we repeat it. Repeat until ... How do I keep repeating? Or when do I know when to stop? Right? I've got a left index and a right index. Right? This one moves over, this one moves over, this one moves over, this one moves over, until they meet. Now when they meet, I still have to check that guy. Is that the thing I'm looking for? If it is, I'm done. What happens on the next iteration? Either the left index goes over or the right index goes over. In which case, either case, what happened to these indexes? They've gone past each other. Right? The left index and the right index. As long as the left is less than or equal to the right, I keep going, right? Repeat until the left index is now greater than the right index. That's my termination condition, right? Once the left has gone past the right, now I know that it was an unsuccessful search. And that's going to end up being phi, my unsuccessful flag value. Let's program that, okay? All right, so I'm going to follow the same thing. Performs a binary search on the given array for the given key element, right? If successful, returns n index at which it finds the element, the key element. Now, why did I say unindex? What if I'm searching for 42 and there are like 5 42s in there? Which one do you end up returning? I don't care, just return one of them, right? And then -1 if no such element, right? So I'm going to steal a lot of this stuff up here. Right? This, I'm calling this a binary search because that's what it is. That's the name of this algorithm, binary search. We'll understand why here. Well, don't have to understand why. Binary, it cuts it in half. It divides and conquers. You can look at it from a recursive point of view, and if you're interested in that, read the book, watch my videos. I'm not even going to bother with the recursion though, because all you need is a simple while loop, right? I need a left index and a right index. Where do I start my left index? 0, right? I need my right index. Where do I start that? Is it at n? Careful. What's the last index in an array? N minus 1, right? While the left index is less than or equal to the right index, that's my continuation condition. I continue going. Once the left index is greater than the right index, that's when I stop and return -1. Okay? So left index is, while the left index is less than the right index, I compute m, left plus right divided by 2. Careful, correct math here. Also careful, this is bad. Risks overflow. So this is an aside, right? We're just going to keep it simple because we're going to use small arrays. But if you had a very large array, say 1 billion elements, or maybe 2 billion elements, and what if you got down to the end of that array, right? And left and right are near 2 billion, right? Let's just say that they're 2 billion and 2 billion. If I add them together, do I get 4 billion? Can you represent 4 billion with an integer? Nope. So this is not the way to do this. The way to do this properly would be the left index plus the right, what is it going to be? Right minus left divided by 2 plus left, something like that, right? That does not risk overflow. It's equivalent mathematically, but it doesn't risk overflow. Right? All right, but I'll leave that in a note there. In fact, that bug, a bug of that type was left in Java for over 10 years, and nobody ever noticed it or fixed it because apparently Java developers don't deal with 1 billion sized arrays at any point. Right? All right, so now we need to look at these 3 conditions. If that's the thing I'm looking for, I'm done. Right? If a sub m is equal to the key, then I'm done and I return m, the index at which I found it. Else if the key is less than a sub m, I need to traverse left. Right? So I need to search the left half. Right? And so m will end up being, or sorry, right gets updated to m minus 1. Right? Just like we did over here. Right is equal to m minus 1. Now the only other case here is else if the key element, or the a sub m, is less than the key element, in which case I need to search the right half. And we update left to be m plus 1. Okay? All right. Well, first of all, do you need this if statement right here? If it's either equal, less than, or greater than, you don't really need that, right? But I'm going to leave it in there for demonstration purposes. Okay? All right, let's see if it works. I'm going to change this to a binary search, right? And we'll search for 42. Oops. not A, what is it? I called it ARR. So ARR, ARR, and ARR. All right. Hey, it works. There's no 42 in that array. And so unsuccessful search means successful test. All right. Let's search for 62, the thing in the end. Unsuccessful search. It's right there. We can see it. Failure. Why didn't it work? What was the operating assumption about this array that allowed us to exploit this for a fast search? It's sorted, right? So we need to understand how to sort now, because as a first step, we need to sort something before we can use binary search. Before we get there, though, let's see if this was even a benefit, okay? What I mean by that is, I mean, we're sunk in the water. Why even bother doing this unless it's faster than linear search, okay? Now, it goes beyond, a little bit beyond the scope of this course to give a formal analysis, but what I want to do is I want to do an informal analysis. How many iterations does binary search end up making, right? Let's start counting them. Well, it certainly makes one iteration, right? Probably makes a second iteration, third iteration, etc. Let's keep track of the size of A. Because remember, what happens here is that on our first search, that's not the thing that we're looking for. We immediately cut it in half, right? And we're only searching 1/2 of it now. So on the first iteration, if it's of size n, then on the second iteration, how big is it? N divided by 2. On the third iteration, how big is it? Well, before it was n divided by 2, now divided by 2. All right. How can you rewrite that so that it's nice mathematically? If I divide something by 2 twice, what do I have? Quarter of it, n divided by 4. Right. Dot, dot, dot. How many iterations do I go? Right. So if I went 3 iterations or 4 iterations or however you want to do this, right? Then it's going to roughly be n divided by 2 to the I. Let me rewrite that. N divided by 2 to the I, right? Where I is your iteration. Now, we're off by 1 here. That's okay, right? Why? Because basically you would, I'll keep it like this. What's the factor down here? It's 2 to the 0. So take your iteration and subtract 1 off of it. Take your iteration and subtract 1 off of it, and there's your exponent right there. 3 minus 2 minus 1 gives you 2, and that's why this is 2 squared. All right? I'm just going to go ahead and ignore the fact that we're off by 1 here. It's going to come out the same. Okay? Now, the real work. What is the work being done? The number of comparisons. How many comparisons do I do on each iteration of this thing? Let's come back over here. All right, I'm in the while loop now. Right? Now there is some addition and division, who cares? There's a comparison right there, a comparison right there, and a comparison right there. But we've already noted that, do I need that comparison? I can get rid of that. I won't, but I can get rid of that. Now, at the end of the day, there are 2 comparisons. But remember, those coefficients out front, that C, right, that quantifies how many comparisons you can do in a second, that's no different than any other constant. So I'm going to go ahead and keep it simple and just say that there's 1 comparison. Because if you said 2, right, that's fine. You'll have a 2 over here instead. Right? On the next iteration, you'll have a 2 over here instead. Right? Whatever analysis comes out of assuming that there's 1, just multiply it by 2 at the end of the day, and who cares? Right? All right. So 1 comparison, dot, 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 1 comparison. Okay? When does the algorithm stop? The size of the array is 1. Right? I like that. Or you could say that the size of the array is 0. Why? Left and right have actually gone past each other. Right? So you could either say 0 or 1. Really doesn't matter. Right? Let's go with 1 though, because the math will come out better. Okay. So how many comparisons do we end up making here? There's the big question. When the size of the array becomes 1, right? I should have written that over here instead. Right? So you tell me, n divided by 2 to the I is equal to 1. I need to find I. This is just algebra. There's no tricks here at all. Right? Now it's no longer algebra. Now it's when would you get introduced to logarithms? That's not trig. It's still algebra, I guess. Right? How do I get rid of that 2? If it was 10 to the n or 10 to the x, how do I get rid of that 10? Take the log base 10 of x, right? If it was e to the x, how do I get rid of that e? Take the natural log of that thing. Right? Now, if you were a mathematician, all of your bases are going to be e. Why is 2.71 the natural logarithm? This is an aside, since we have time. Right? Why do mathematicians think that e to the e is the natural log? Think calculus. What's the first derivative of e to the x? E to the x. It's the value at which the first derivative has a coefficient of 1. Right? What if we did this instead with, say, 2 to the x, and I took the first derivative of that? It gets ugly, because you have to convert it to using the change of base formula, and you would end up with something like 1 over natural log of 2 to the x. That's ugly. I've got this thing sitting out front, and all my equations now I've got to write way too much. This is why mathematicians like this. It's the only value, base value, that gives you a coefficient of 1 for your after your first derivative. Right? This is definitely not 1. Right? This is some random value, whatever. Right? But we are self-respecting computer scientists. All of our bases are 2. Why is that? Does a computer think in 2.71 numbers? There's no such thing. Does a computer think like a human? Base 10, because of 10 fingers and 10 toes. No. Our computers they don't actually think, but our computers think in base 2, on, off, 1, 0, high voltage, low voltage, right? Etc. So we will take the log base 2 of n is equal to I. That's the number of iterations. And again, self-respecting computer scientists, anytime that we write log of n, we mean log base 2. It doesn't matter, because you can always use the change of base formula, right, from your algebra days, right? Change of base formula, log base b of a, or x, is equal to log base a of x over log base a of b, something like that. Right? Question mark. I don't know if that's correct or not from my memory. Right? But you can always change it from log base b into log base a simply to within a constant. Okay. All right. So the total, my observation here is going to be that the number of iterations is equal to the number of comparisons, which is equal to approximately, off by 1, whatever, log of n. Now, what is the relationship between linear search and linear search? We'll just say that that's n, right? And then binary search, log n. What would I have to do to this thing right here in order to recover n? What if I went from this to this? I would exponentiate it. It would be 2 to the log n is equal to n. In other words, this is exponentially faster, right? An exponential speed up. Look at it from another perspective. N versus log n from a calc perspective, right? We already looked at there's a constant rate of growth. Right. There is a good question. What's the first derivative of log base 2 of n? I just did it, didn't I? I gave it to you, right? It's 1 over natural log of 2 n, right? Which is some constant times 1 over n. What's the rate of growth of that thing? As n tends towards infinity, what happens to that denominator? It gets bigger, bigger, bigger. Because it's in the denominator, what happens to the entire thing? It gets smaller, smaller, smaller. In other words, the rate of growth goes down. Right. So if you've ever seen a logarithm, it starts out high, but then it's always going to be monotone, increasing. It's going to go off to infinity, but it's going to grow very, very slowly, right? Okay. So constant rate of growth versus a diminishing rate of growth. That's way better. Look at it from a algebraic perspective. If I went from, if n took time t, suppose that I went up to 2n. What time does that take now? It's not going to take 2t because it's no longer a linear function. Instead, it's going to take log of 2n. Now pull out your log identity memories. Right? What is log of a b? Log a, I don't have a here. Log n plus log 2. Right? All I did was switch these around and then split it up, right? Because they were multiplied together, right? That's what it was before. T plus, what is this thing right here? Remember, it's implicitly base 2. So it's going to be 1. It's not twice as slow. Instead, it's just one more comparison. If you go from 1 million elements to 2 million elements, all you need to do is one more operation. That's it. If you went to 10 million, 10n, right? Went from 1 million to 10 million. Same thing here. Log of 10, n, is going to be log of n, which is as t as before, plus log base 2 of 10. That's like 3, right? So it's less than, just 3 more. 10 times as big, but you only need to do 3 more things. Right? You went from 1 billion to 10 billion. You only need to do at most 3 more comparisons. Right? This is a huge benefit, right? Instead of doing, say that my input size here is, say, 2 trillion, or that, let's just get it, say 10 trillion, right? Trillion. Right. Then n would be 10 trillion comparisons. That's for linear search. But here, log n is equal to log of 10 trillion, which would be 10 to the 9th, right? That's 1 trillion. Correct, right? No, that's 1 billion. 1 trillion would be what? 12. There we go. Sorry. All right. Now, again, pull out yet another log identity. Log of x raised to the power y. What happens to that power y? It's pulled up front times log base 2 of 10. And so this is less than, say, 40, right? I'm just overestimating there. It's going to end up being like less than 36. 10 trillion comparisons versus 40 comparisons. Is it obvious now that it's worth it, right? In fact, this is probably not doable in a lot of situations, right? So what we need now is sorting, right? It doesn't work if it's not sorted, right? So we've got to sort it now, right? And that's where we'll pick it up on Friday. Okay. All right. Have a good day.